Hello, AP Stat students. Today we're going to continue our discussion of linear regression, and today we're going to focus on a term called the coefficient of determination. It's denoted as r squared. So yes, it is the square of the correlation coefficient. Remember, r is the correlation. Okay, so squaring r gets you r squared. And r squared has a special meaning in linear regression that we'll talk about now. This is one of the tougher topics to really understand in this unit, so pay attention and maybe watch the video twice if you need to. But here goes. So the table below shows the GPAs of 10 students. Okay. It says, imagine we had an 11th student that was not included in the data, and we wanted to estimate their GPA using the information that we have. What would be a logical estimate of this student's GPA if all we had to go on was the data set below? Well, what I did here is I graphed all the GPAs. So, and I just called the first student student 1, so this would be student 1, and you can see their GPA was 3. Okay, and then I just graphed a point for every student's GPA, and there were 10 total. So you can see the 10th student is right here in the chart. That was 2.4. Okay, so you can see there's a wide range of GPAs for these students. But if all I had to go on was these 10 pieces of data, and I had to guess or estimate or predict what this 11th person, what their GPA might be, I think a logical conclusion would be to find the average of these 10 people, okay? And I actually put in the average line right here. Okay, so the average GPA was just a little above 3.0, okay? And you can see that line pretty much just cuts that data in half, and you can see there are residuals, right? We've been studying residuals. If you added up the residuals, both positive and negative, around that average line, they would add up to 0, which is pretty cool. Okay? So, I use the average to estimate this 11th person's GPA. Now, obviously, all 10 students do not have the same GPA. Their GPAs vary around the mean GPA. And we can measure this variation by adding up how far away each GPA is from the mean. Unfortunately, remember, those distances will add up to 0 because they are residuals. Okay? So if you remember, what we can do is we can square all those residuals, because then the negative ones become positive. Okay? And you can see I took every residual here and squared it. So like this is the residual for that point. And then when I square that, I get a square with that area. Okay? Now, after I squared all those residuals, I added them up. And the sum of those residuals squared is 1.596. Okay? So you could call that number the total sum of the squared deviations from this data around the mean. It's a measure of how much the GPAs vary around the mean GPA. Okay? And the mean GPA, I have it here on the chart, is 3.02. So that would be our guess for the 11th person, okay? You could consider this 1.596 to be kind of like the total error possible in our estimate, okay? And it's the error squared, okay? So just using the average to make a prediction, I'm going to have about that much error in that calculation, okay? You can think of it that way. Now, suppose we go back and ask the 10 students what their IQ scores are, and we add them to the table, okay? So I know what their GPAs are. Now I'm going to ask each person, hey, what's your IQ? Okay, so now I have the same 10 people. Person 1 would be here, but notice now I have an IQ and a GPA. So now instead of using person number 1 and making a graph, person number 2 like we did last time, I'm going to use their IQ as the explanatory variable, or the X variable, and their GPA as the Y variable. Okay? Well, now if you look at it, there seems to be a positive, strong linear relationship between those two variables. And it looks like as IQ increases, so does GPA. Okay, which would make sense. IQ is a measure of intelligence, and I would think that the more intelligent you are, probably the higher GPA you had, all things being equal. Okay, but now notice that instead of the average GPA being our line, now I use a least square regression line as our prediction line. So instead of the average, now I'm using the least square regression line. Okay, so now our predicted GPA comes from someone's IQ value. Well, how much variation is there using this model to make predictions? Well, just like before, I have residuals, right? Like these are residuals. So how far off the actual GPA was from the predicted GPA using IQ. And again, if I added all the residuals up, they would cancel out. So I square them and add them together. And now the sum of all those squares is only 0.2662. Okay. So notice I've dropped the total amount of error. And remember, it's error squared, really. But I've dropped that error quite a bit, actually. Okay. So 0.2662 is the total sum of the squared deviations for this data. It's a measure of how much the GPAs vary around the least square regression on IQ. Okay. But let's check this out. How much of our original variation have we accounted for now with the IQ data? Remember, we originally had this much variation when all we were using was the average GPA to make our prediction. Now we only have 0.2662 units of variation. So if I subtract off how much variation we had originally minus how much we have now with our regression, I get this, 1.3922. Okay, that's how much of the variation we have eliminated. Okay, by using IQ to make our prediction instead of just the average. And now this is the cool part. This variation eliminated divided by how much variation we had when it was just IQ, that is R squared. Now, so from where we started, we have accounted for this much of the variation, which is 0.83. Okay. Now, the original correlation for this association was 0.91. That's for the IQ GPA regression. If you square that, you get 0.83. And just for effect here, notice those two are the same. Okay? So, what we just found is called the coefficient of determination. It is denoted as R squared. And yes, that's the correlation coefficient, R squared. Okay? So, the definition of this, it's a measure of how much of the variation in our data can be accounted for by our regression on the explanatory variable. So in other words, it's how much of the variation in GPAs I can account for based on our regression with IQ. So I can account for 83% of the variation, which is fabulous. I've almost accounted for all of it. Okay. The only way I would ever account for all of it is if IQs and GPAs lined up perfectly in a straight line so that the R was 1, because then of course R squared would be 1 also, be 100%. Okay. But this means we've done a pretty good job of getting rid of the variation. Okay. Obviously, if we're going to predict GPA, instead of using the mean as our prediction, we'd rather use this linear regression with IQ. It makes a much better prediction. We can account for 83% of the error that way, okay? So another way to think of R squared is the proportion of the variation in the y values that is explained or accounted for by our least square regression on x. And of course, in statistics, we won't just call them y and x. We will use terms from the problem. So we would say something like the proportion of the variation in GPAs that's explained or accounted for by our least square regression on IQ. Okay, so we replace those. So in other words, R squared is a measure of how much of the variance of y is explained by the model. And our model is the equation. And R squared of 1 indicates that the regression line perfectly fits the data, and the regression accounts for all the variation in the response variable. That's a wonderful situation if it happens, but in real life data, it's rarely are you ever going to see an R squared of 1 or 100%. And R squared of 0 indicates the line does not account for any of the variation in the response variable. Obviously, in that situation, we would never use that line to make a prediction then, because it's simply not going to be accurate at all. Okay. Along with the slope and the intercept for a regression, you should always report R squared so that readers can judge for themselves how successful the regression is at describing the relationship. Okay. Statistics is about variation, and R squared measures the success of the regression model in terms of the fraction of the variation of y accounted for by the regression. Now, here are how you would describe this if you were answering a question. So you'd say some percent of the variation in the y variable is accounted for by the least square regression on the x variable. Or you can say, a certain percent of the variation in the y variable is explained by the least square regression on x. So you'll see both of these words used, accounted for and explained. So if I was going to write the interpretation of R squared from our IQ versus GPA regression, I would say one of these two things. Either 83% of the variation in GPA is accounted for by the least square regression on IQ, or we'd say 83% of the variation in GPA is explained by the least square regression on IQ. Okay. One way to think of this is that looking at GPA and IQ, IQ does a pretty good job of predicting GPA because our R squared was 83%. But it's not perfect, okay? There may be some other factors involved when I'm making this prediction, okay? Like what else could predict your GPA? Maybe your class load, like you're taking a lot of classes, you might not have as high GPA. How much homework you do, it affects your GPA, right? In high school, parental involvement makes a difference. Like how much are your parents bugging you to do your homework? That makes a difference, okay? So IQ is not the only thing that affects your GPA, but it does get rid of about 83% of the variation in IQ. Now 17% comes from somewhere else, okay? And maybe it's a combination of these factors, okay? So we want that R squared to be as high as possible because it means that we've accounted for the most variation possible, okay? But realize because it's not 100%, it means that there's other variables out there that are probably contributing to this relationship, okay? As you're doing problems with these, most of the time on the AP exam, this will be a multiple choice type situation, and you'll have to choose the correct interpretation. So things we're looking for are this 83% of the variation. That's how they'll say it every single time. They'll be talking about the variation, and then they'll use the accounted for or explained, and they'll always talk about the regression on the other variable, okay? So if you see that kind of thing, you know they're talking about R squared, which is the coefficient of determination.